Okay, so in the previous two videos, we've been talking about classification of equations. We've talked about how to determine if an equation is differential or algebraic. And under the umbrella of differential equations, we've talked about first, second, third, nth order differential equations and constant or variable coefficient differential equations. These last few that we're going to talk about do not fall under the umbrella of just differential or algebraic equations. Either differential or algebraic equations can be classified in these ways. Um, so the first one we're going to talk about is homogeneous versus inhomogeneous differential equations. So an equation is homogeneous if all terms of the equation contain one or more dependent variables. So for example, if you have x plus y, which is equals 0, which is an algebraic equation, um, every single term, 0 not necessarily counting, uh, contain a differential or contain a dependent variable, assuming time is our independent variable. So this one is homogeneous. It's a difficult example to start with. Um, on the other hand, if we said x plus y equals t, this is also a differential equation, but this is an inhomogeneous. Make sure that's legible. Algebraic equation. This term right here, the t, is just an independent variable. There are no dependent variables in this term. Another example, if we were to say t squared x double dot plus sine of t x dot squared plus x equals 0, every single term here contains a dependent variable. Here you have the t squared x double dot contains x double dot. Sine t, sine of t times x dot squared contains the x dot squared, and then x contains x. So this is a homogeneous differential equation. Often, what you'll see is that the inhomogeneous terms, the terms that do not contain the dependent variables, excuse me, will be on the right-hand side of the equation. So often they'll be written with your homogeneous terms on the left and your inhomogeneous terms on the right. Another classification that can apply to differential or algebraic equations is linear or nonlinear equations. Um, so we're talking about linear in our dependent variables. An equation is linear with respect to its dependent variables if the dependent variables, I'll write this out, dependent variables and their derivatives I can spell, are only multiplied by coefficients. So from the algebraic sense, by constant coefficients. Sorry, coefficients. So from the algebraic sense, we have the equation for a line, y equals mx plus b. In this case, our independent variable is y, our dependent variable is x, and the dependent variable x is only multiplied by the constant m. And so this equation is linear in x. So in general, for a differential equation, you can say that some constant c0 plus some constant c1 times x plus another constant c2 times x dot plus another constant c3 times x double dot equals 0, or it doesn't have to equal 0. It can equal some function of t. This equation is linear in x because each time x appears, or x dot, or x double dot, and so on, it is only multiplied by a constant. A nonlinear equation is going to be anything else. If you start to see any sorts of terms like x times x dot, or x squared, or cosine of x, all of these are nonlinear terms and they make the entire equation nonlinear. So I'll say this one is linear and this one is non-linear. You can have, I guess I should say, not necessarily, these coefficients are not necessarily constant, but they do not involve the dependent variables. They do not involve x. So we can have a constant or a variable coefficient, excuse me. So if you said t times x double dot plus t squared x dot plus cosine of t times x, x is not multiplied by anything that involves x. And so this, say it's equal 0, this is a linear function in x. But it's a variable coefficient. It's a variable coefficient linear ordinary differential equation. Finally, and this is very similar, well, not necessarily similar, but along the same lines as linear versus nonlinear, we have uncoupled versus coupled equations. And this has to do with systems of equations. So we're talking about coupled in our dependent variables. So if our dependent variable shows up in more than one equation in a system of equations, then it is coupled. So I'll say it's coupled if your dependent, and I'll just shorten it, dependent variable shows up in greater than one, more than one equation in a system. So if we have something along the lines of t squared cosine of x cubed plus sine of t x squared plus x equals 0, and in that same system we have y plus t cubed sine of y equals 0. This is an uncoupled system. In the first equation, you only see x as the dependent variable. In the second equation, you only see y. If, on the other hand, you have a system that says x plus y equals 0 and x equals 7, this is a coupled system. Specifically, it's coupled in x. X shows up in more than one equation in the system. So we'll go ahead and take a break from there.